Hello Year 9. Welcome back to a fine Saturday night of mathematics. This lesson is purely about similar triangles. So the previous lesson was looking at similar objects generally. How can we tell if an object is similar, meaning they're the same shape but a different size? That previous lesson we looked at, well, the concept of similar objects, how we could tell if an object was similar or not, and we then looked at the use of scale factor and using scale factor to find unknown side lengths in similar objects. So today takes this a little more specialized. This lesson we're only looking at triangles. Now when it comes to triangles, there are 4 very specific tests that we can use to see if triangles are actually similar. And that's what you see the start of behind us here. I've written up the rules for how you can tell if triangles are similar. But you may be looking at that and going, what on earth does that mean? Or on the other hand, you might already be familiar with it. I don't know. You're not responding for some reason right now. Now, here, I'm just going to go through the rules, all right? If all side lengths are in ratio, the same scale factor can be used to go between the triangles. We can say that those triangles are similar. SSS stands for side, side, side. And we should see the same ratio, in other words, the bigger value divided by the smaller value in this case, between all side lengths for that to work. So in this case, these sides are equivalent. You see I've drawn them right next to each other. They're the same shape and I haven't turned them around or done anything fancy this time. 18 divided by 6 is 3. But so is 6 divided by 2. And so is 15 divided by 5. All of them give the same ratio of 3. If for any side length I was going from the smaller to the bigger, I'd multiply it by 3. For any side length going from the bigger one to the smaller one, I divide it by 3. There is the same ratio for each side. Thus, all the sides are in agreement, and hence we say these two objects are similar by the rule SSS. The next rule you can use is SAS. I didn't draw that convincingly the same there, did I? Needs to go out a bit more. Right, do you want to have a guess what SAS stands for? Side, angle, side. So if you have two sides in ratio and an angle between them, you can use this rule. So if I had an angle here, let's say that's 62 degrees, it'd have to be the same angle over here, and I had the sides around it. So if that was 4 to 8, and this one here was 7 to 14, you notice that, again, 8 divided by 4 is 2, 14 divided by 7 is 2. As long as you've got that same ratio, this rule applies. Now the trick with this rule that you need to remember is that A is not by accident between the two S's there. Right? It's meant to be read side, angle, side because the angle must be between the two sides, right? Angle must be between the two sides you are comparing. Right? So some students express disappointment about that because they don't get to rearrange SAS to be something else that they would prefer to be writing on their books for some reason. But no, it's got to be SAS. You can't do other combinations like SSA, okay? So these two triangles we could call as being similar by the rule SAS. The sides are in ratio and they have the same angle in between. Third rule, where you could decide if two triangles are similar. You want to have a guess what that stands for? Angle, angle, angle. running out of room, so I might not draw a picture here. But if you have two triangles that have all the same angle in them, they're the same shape. They don't have to be the same size. They can be completely different sizes with the same angles. But if they've got the same angles, they are similar. I'll spare you a drawing on that one. You can always grab it from the text if you want. RHS is a little bit different. This means that it's a right angle triangle. A right angle triangle where you have the hypotenuse and another side. So RHS stands for right angle hypotenuse side. If you have two triangles that have them in common, then they are similar. So for example, here I'll do a right angle triangle. We need to have the hypotenuse, I'll call it 6, and we've got to have one other side. I might call it 3. All right, and if you have a bigger one, that's again a right angle triangle. What ratio do we want to use? I'll use a ratio of 4 this time. So if I multiply everything there by 4, I'd get that triangle. So they're both right angles. You have the hypotenuse for both. Scale factor of 4, longer length divided by a smaller length gives me a scale factor of 4. And I also have a side with a scale factor of 4. We can say that these two are indeed similar by the rule RHS. The other thing you need to be able to do is write something called a similarity statement. These things look like this. So it'd probably help if I put some labels on this. Let's call this triangle A, B, C, and I'm going to call this one D, E, F. If I was to say that these two triangles are similar, the way I'd write that in symbols is to go triangle ABC, referring to the corners. So that's triangle ABC is similar, 3 vertical lines, meaning is similar, to DEF, where, yeah, DEF is this triangle here. Notice that I've even made it so that A is the equivalent of D, so they're at the same place. B is the equivalent of E in the same place. C is the equivalent of F. We should try to do that. Now, there's a second way you can write it that means the same thing. The tilde that you will see on often towards the top left-hand side of your keyboard, you can also use that to signify similarity. So you can use the vertical lines or the tilde for similarity. Either way, this is a similarity statement. You will look at some point and stare at me and go, what is a similarity statement? There it is. 2 different versions. I will accept either. I love either. It's all good. They are similarity statements. Right, so let's use this stuff in a couple of examples and then I shall let you go and be free to complete what you wish to do in this area. So hope you've got all that down because it's going. Except the top row. We might spare the top row. Right, so are these similar? If so, provide a rule. Right, so I'll do that one and I'll do that. No, that doesn't look the same at all, does it? Let's try that again. There, there, there. Don't mind me. I've got to have some of my dinner here. Doritos. That's Teacher Life. And I'm going to put 16 centimeters on here. 12 centimeters here. And I'm going to put 38 degrees in here. There we go. So the question is, are they similar? So let's look at what we've got. For both of these, we've got a side, and an angle. A side. Now, one of our rules looks a bit like that, doesn't it? Happens to be called SAS. So my leaning is to think, well, these might be similar under SAS, but I first need to compare the sizes here. So let's check you've got the same ratio. So if I compare the equivalent sides, check side ratio. I've got 24 to 12 here. So this is really the scale factor. By looking at those two sides, I get a scale factor of 2. And let's look at the other two sides there that we've got the equivalent of, 32 and 16. 32 divided by 16 gives a scale factor of 2 as well. Looking good. We have side angle side, and those sides are in the same ratio. So therefore we'd say yes, similar, by the rule SAS. I'll put some labels on it. So let's say this was X, Y, Z, and this was B, A, D. It's bad. Right? If you were asked for a similarity statement, you would be writing something like triangle X, Y, Z is similar to triangle, and instead of X, there's B. Instead of Y, there's A. Instead of Z, there's D. So my similarity statement for this one would read something like triangle XYZ is similar to triangle BAD. All right. That's the same process you need to use for all your checks. Look at what they've got. Check they've got stuff in common. Compare those sides. They've got to be in the same ratio. Right? If that was something like 30, they wouldn't have been in the same ratio, right? They have to have the same scale factor when you compare those sides, or they are not similar. So we'll probably do one last sort of test question. All right. All right, so I'm going to do something like this. All right, so I've got a right angle triangle there. And what are we going to do? So, all right, let's make this 8 meters. We're going to make this bit here 6 meters. And the question is going to be, let's assume these are similar objects. And what are we going to make that over there? They're not similar objects. That's the problem with that diagram, isn't it? Scrap that example. Remember similar objects. Similar objects are the same shape but a different size. They're actually a different shape, so it was shaping up to be a really bad example. All right. So what we're going to do is we're going to have a 1.8 meter tall person, and a particular time of the day, they had a 80, I'm going to make this one harder, right? An 80 centimeter shadow. And you're going to be told they are similar. And we want to know we have someone who's 1.5 meters, and we want to know what sort of shadow a 1.5 meter person would have at the same time of the day. Now you can probably logically work that out. A lot of people will. So what shadow length will a 1.5 meter tall person have when a 1.8 meter tall person has a 1.8 has a 80 centimeter shadow. So that's our predicament. Now, the reason you can use these concepts that we've just been covering on this question is because these two are actually similar triangles. So that's, why are they similar though? Because the angle here will also be in common. Right? We're assuming the angle of the sun is going to be the same, isn't it? So the angle up the top there will be the same. And in any triangle, if you have two angles, what does that mean about the third? If you have two angles, you always know the third angle in a triangle. If those two angles are the same, that angle is going to be the same as well. So you could know, and that's what's tricky about a question like this. Angle of the sun will be constant. Thus, all angles will be the same. So those two triangles are similar by the rule AAA. Angle, angle, angle. You might not have seen that initially. The question doesn't necessarily give that away, does it? Tricky. That's why it's not a C-level question. To find the length there though, we can simply find the ratio between the two triangles. So the scale factor, remember how I said for scale factor you should use the larger value divided by the smaller one? So larger length divided by smaller length. The comparable length that we have in both these triangles is this one here. We have 1.8 divided by 1.5. What's that, 1.2? Am I expecting 1.2 here? Yeah, 1.2. So the scale factor is 1.2. Now, to get from a larger dimension to a smaller dimension, what do? Do we multiply or divide if we're trying to get a value in the smaller triangle, the smaller object? That's right, we divide. So I might call this x. X is going to be our 80 centimetres. You know what? What's interesting here is I can leave it in centimetres. It doesn't matter whether I do this in metres or centimetres. I am going to get the correct answer. I'll leave you to think about why. But if I do 80 divided by the scale factor, because we're going to get a smaller value here, 80 divided by 1.2, my calculator shows a recurring in a strange way. It'll be 66.6 recurring centimetres. So the shorter person, the 1.5 metre tall person, is going to have a shadow of, well, nearly 67 centimetres at the same time of the day. Right, so that's it for this lesson, guys. The basic facts are, similar triangles. There are a series of tests that you can use to check whether triangles are similar. They are, what were they? SSS, SAS, AAA and RHS. You need to be able to recall them, be able to use them to check if triangles are similar, and then use those principles to find unknown side lengths. This is a harder question. There's a slightly easier one in your text if you want to review that. Go forth and triangulate and things. Bye.